title is a little misleading. I would rather say it's about entropy and geometry of distinguishability of quantum states. And this work we've been doing for past 1 hour and with Sam, Suparna and Kumar Shivam. So yeah, this is the outline of my talk with the introduction and relative entropy as Riemannian metric and thermodynamic relations and measurements and what we call quantum advantage. So this slide would contribute to what gave us motivation towards this work. So this is a chromaticity diagram which contains the space of colors. And here what these ellipses describe is, ellipses are called MacAdam ellipses. These describe the metric on the space of colors, on the ability of a human eye to distinguish these colors. I mean, any color on the ellipse is equally distinguishable from the center, and any color inside is indistinguishable from the center of the ellipse. So the idea is to come up with a similar thing for quantum states, which a metric which tells us what is our ability to distinguish quantum states. So for that, okay. So what do we mean by distance measure? If you are given any two states, quantum or classical state, how similar or different are they? And by state we mean probability distribution or density matrices. And few examples would be fidelity, trace distance, Hilbert-Spitzname and other things. But what does they signify in reality? What does this signify? So for us, the base would be, base turn out to be relative entropy to go further. So these are the formulas for relative entropy, and the properties would be it is always positive and it's zero only when probability distributions are same or when density matrices are same, and it's not symmetric. The problem with relative entropy is it's not a true distance. It doesn't follow triangle inequality or it is not symmetric. But the reason for choosing relative entropy for going forward is its connection with likelihood theory. So let's assume you have a biased coin. The probabilities are not half-half. So you come up with your own probability distribution for the coin, something else. So which is described by Q here. And you toss it a few times and you get some certain number of heads and certain number of tails which are described by C. So what likelihood theory tells is that what is the probability that your observed histogram has been obtained by your modeled distribution. So and likelihood theory is related to relative entropy with this formula. So in other words, what does it say is how many tosses you have to make of a coin to tell with certain confidence that whether your model distribution is right or wrong. So that's the reason why we choose likelihood theory. So going forward, so we write relative entropy for two density matrices S of rho 1, rho 2. And what we did to get a metric on this space is we took rho 2 in the neighborhood of rho 1 and did a Taylor expansion. So as Taylor expansion around rho 1. So S of rho 1 comma rho 1 and first order and second order terms. These two terms goes to 0. S of rho 1 comma rho 1 is 0. And since this is an expansion around the minima of the function, this term also goes to 0. The only term survives is this. And we neglect the higher order terms. And this actually serves as our metric here, Gij. And so after this, we have calculated a distance function in case of using this metric. We calculate distance function for qubits. Any qubit can be represented using a vector on a block sphere. So this would be a block sphere, and if I have a state, it can always be represented by a three-dimensional vector n bar. So for a qubit, when we calculated distance function, we have got this ds square is equal to d alpha square plus f of alpha d omega square, where f of alpha is given by this function. And if you observe, there is a spherical symmetry in this term. So from now onwards, I would restrict our calculations to a plane where the states are lying down, because there is a spherical symmetry. I can always replace this with just d theta square. So this would make my calculations a little more easier. So yeah, so this is just a equation. Okay, this gives us a scalar curvature for our metric, which is always, it starts at 0, which as a flat space, and it goes to minus infinity as r tends to 1. So it's always negative. So whatever distance we have got is a true distance. And these are the geodesics for our metric. I mean, we have taken 2 random points selected and try to draw a geodesic through this, and 2 other geodesics to see whether the thing is, for any metric, if the curvature is negative, any 2 geodesics does not cross each other more than once. So this is one way to check that. So yeah, one thing we have observed is that this metric has thermodynamic implications towards it. That is, we have whatever states rho 1, rho 2 we have taken to be Gibbs states in this case, where when we take in rho 2 in the neighborhood of rho 1, the similar way, the Hamiltonian H2 can be taken as perturbed Hamiltonian H1 with epsilon v as the perturbed term. There we have observed their connection with relative entropy with the free energy. So that connection gives us this formula, Gij into this equal to, some constant that equal to second order correction in free energy. So whatever metric we have got, that metric at any given state in the given set, not just 2-dimensional, any higher dimension, tells us the correction term, the second order correction term for the free energy of the state. So next would be the projective measurement. So let us assume that we are given n qubits of the all same state. So how do I tell that what state it is in? I have given state some n qubits of one state, either it is in rho 1 or rho 2. So I have to distinguish, by doing measurements. So if, this is a measurement axis for which I'll be getting probabilities, and that would be turning out to be p plus minus, q plus minus for rho 1, rho 2, and for that relative entropy would be given by this classical relative entropy. So for a certain example, we have checked how quantum relative entropy would be and classical relative entropy would be there. This is the classical relative entropy, and this is the quantum relative entropy for the particular example we have solved. It shows that even the maximum of classical relative entropy optimized with this angle beta, that is by changing m for different directions, it does not reach classical relative entropy. So there is more to it than, there is something we are missing in while making projective measurements, which we thought there is a necessity to explore. So yeah, one more thing. So this gap which is there, we are calling quantum advantage we have. So S star is the maximum that is available in this case, and S is the quantum relative entropy. And this graph shows us that for any given R1 and R2 of 2 states, I just vary the angle theta, and this is quantum relative entropy, and the bottom one is classical relative entropy optimized. And if you see for theta equal to 0 or around pi, there is no quantum advantage. That is, when states commute with each other, there is no quantum advantage, and this gap always occurs when states do not commute with each other. So we try to find this gap, try to do it analytically, which we couldn't do for relative entropy. So we had to go for infinitesimal case, again trying to find it in the form of metric and everything. So that gave us actually, when we try to optimize the classical metric, that gave us Bourret-Helmstrom metric, this one. So this is a new way to look at Bourret-Helmstrom metric, where earlier people have gotten it completely mathematically, where we have got in terms of projective measurements. And this is the same MacAdam ellipses I have shown earlier in the space of colors. This is in the space of quantum state. I have taken a slice in block sphere, and these red ones describe for the metric which we have gotten, and the blue ones describe for the Bourret-Helmstrom metric. And here if you see the comparison between these two, this Bourret-Helmstrom metric covers a larger area. That is, from the center, more states are indistinguishable. That meaning that in this, in case of BK this R metric, that is, it distinguishes much better than the other metric. So how do we explore whatever is available to us between those two states? So the idea is to, rather than making measurements on one state at a time, one qubit at a time, what if I make measurements on 2 qubits at a time? So I have n qubits, so I'll make measurements 2 qubit at a time in this, in product-Hilbert space, that is rho tensor rho. The reason behind doing this is that when I take a product-Hilbert space, there are large number of states available for making measurements, like for example, Bell states. So initially we have taken all the 4 Bell states to get the probabilities and make measurements, but it didn't show us any improvement from classical probability. So we had to do some trial and error and other things. So where we ended up with 2 Bell states and 2 separable states, so which actually gave us improvement. So this S describes the quantum relative entropy. This S star gives us classical relative entropy optimized. So when we measured in this B basis, this is what the relative entropy which we got, which there is a slight improvement. But one doubt we had is it the best we can do? So we wrote a program using Monte Carlo algorithm to explore all the states available in the product space. So numerically optimizing that gave us one more value which is improvising on this basis either. So, and then again we did the same Monte Carlo method for 3 measurements on 3 states at a time. That has shown us much more improvement. So our idea is if we have n states and we make measurement on all the states at a time, that should, as n tends to infinity, that should give us quantum relative entropy. I mean, usually if you are making just measurements on one state at a time, you just get probabilities as n tend to infinity, but here you will get classical relative entropy directly as we make measurements many states at a time. So is this experimentally possible? Because making measurements on Bell state, I don't know whether it is possible or not, so we try to look at it in a different point of view. I mean, it looks like it is possible with using cold atoms, but the theory behind it is these separable states and Bell states are connected through a unitary transformation U. So rather than applying U on the states to, rather than applying U on the separable states to get a Bell state, rather than I would apply on this state and make measurement on the separable states, which would give me the same probabilities. So this is the idea to, I mean, this is the way we think we can explore the quantum advantage which we described. So thank you.
Third one, yeah. Can you explain to me why it's not symmetric?
Relative entropy.
Yes. Yeah. So if I compare state P with Q, I get one number, but if I compare state Q with P, I get a different relative entropy.
Yeah, yeah. The reason, because there is in relative entropy, you have a modal distribution and you have a actual distribution. It is comparing, you have a reference state there. I mean, in that sense, that's why people don't prefer relative entropy that much, because it's not symmetric, whereas our metric, that's why we gotten ahead to get this metric from relative entropy, which is actually symmetric. The reason why it is not is, the first one talks about the reference with respect to which you are making a measurement. In other terms, it would talk about, if you are talking about coding, it would like how much more information you require to code this probability in different manner. No, it's rho log sigma. If it is rho log rho minus sigma log sigma, it would be symmetric with just a negative sign.
So I'm afraid I missed the first few minutes of your talk, but is it correct that you've defined a new metric on the space of density matrices? Or this is actually a metric that people have already considered?
Initially, when we started out, we did not know there is a...
This looks like a familiar one.
Yeah, this is actually a familiar. Initially, when we started out, we thought it was new. We did not know there existed a metric. Just before writing up the paper, we came to know there existed a metric called BKM metric with the same structure.
But something, yeah, okay.
It's called BKM Bogoliubov-Kubomori metric.
So the reason I asked is that there's this other metric that I think you also considered called Bour's metric or something like that.
Yes.
And someone, I remember hearing this, but I don't remember the details, but maybe you will remember, that the reason that this other metric is in some way better than the one that you're using is that it extends nicely to the, without a divergence, to the case of degenerate, where the density matrix has some zeros, right? So in the classical situation, this Bhattacharya metric, or whatever you call it, the analog of this, that makes the space of states into a nice portion of a sphere. So it makes it a nice manifold, even when some of the probabilities are zero. You see what I mean? When you're at the edge of the simplex of probabilities.
Yeah,
I remember that that's not the case for the quantum. Is that right? Do you regard it as a weakness of this metric?
This one actually for the one of the eigenvalues also turning to be 0 would be, there is some other metric with the similar structure, but just by making a transformation r is equal to sine alpha, this singularity can be removed in this case. Whereas in this metric, it cannot be removed. We tried doing different stuff, but it looks like a true singularity which cannot be removed. I mean, in case of pure state, it always diverges.
You could check it by computing the scalar curvature or something, and showing that it blows up. But are you saying that
scalar curvature here, it does blow up actually, it goes to infinity.
Right,
as for this actually we have checked, it is actually constant negative scalar curvature.
Or just 2 dimensions, is it? Okay, well we can
confined our calculations to 2 dimensions.
I remember someone telling me that that's not the case with this, but maybe you have to go to higher dimensions to see the divergence. Or maybe I'm remembering, maybe you have to go to infinite dimensions. There's some claim that this one has that same divergence.
Okay.
Unlike this BH, what you call BH metric.